Okay. So following right on the heels of talking about isotopes, I can now talk about masses of atoms. So I just want to clarify, I want to make sure all of the terms are really clear to you. Mass number, which we've talked about previously, is not an actual measurement. It's just a tally. It's how many protons and how many neutrons. The mass number is just sort of, it's almost like a name we put on a given isotope so we can differentiate it from other isotopes. It's always a whole number. So that's a mass number. And it's one way to distinguish an isotope from another. I'm now going to start talking about actual measured masses of atoms. So this is different from mass number. And this is going to link us to those numbers in the periodic table here. So this is going to link us here to these numbers. So we need a new unit. Since I can't really talk about them in terms of grams, we have ridiculously tiny numbers, exponents of like -21 and 22, and it's just kind of insane. So a new unit is going to be developed. Well, it has been developed, and we're going to talk about this new unit called atomic mass units, or AMUs. Here is the definition. This is how an atomic mass unit is defined, right? So 1 AMU is the mass of a carbon atom containing 6 protons and 6 neutrons. So what is the mass number of that carbon atom? Right, it's 12, right? Because there's 6 protons, there's 6 nucleons. Now I've got to ask you, where does most of the mass of this carbon atom come from? The electrons, the protons, the neutrons, what? Hopefully you said the nucleons, right? Now do you remember back, how does the mass of 1 proton compare to the mass of 1 neutron? Do you guys remember? It turns out that there are to at least 3 significant figures, they are the same. So I should maybe write it this way. They're pretty much the same. So this AMU, this unit, is defined as being 1/12 the mass of 1 carbon with 12 nucleons, and these nucleons are what make up most of the mass. So if you think about it, 1 proton is going to have a mass of about, more or less, 1 AMU. And 1 neutron is going to have a mass of about 1 AMU, right? So carbon-12 is going to have a mass of exactly 12 AMU, right? Now, because this is based on the carbon atom, other elements, other atoms, other isotopes are going to vary a little bit. So this is all based on carbon-12, so they're all going to vary a little bit. So what you're going to see is the mass of an isotope is going to be very close to that of its mass number. So it turns out that this is actually an AMU here. An AMU has roughly, 1 AMU is the mass of roughly 1 proton or 1 neutron. This is actually what they are. 1 proton is actually 1.0073, and a neutron is 1.0087. And you can see that if you go enough significant figures out, their mass is slightly different, but not a lot. So what's going to happen is that one mass, there we go. So the atomic weight, or the atomic mass of a given isotope, or a given single atom, is nearly that of the mass number. So all naturally occurring phosphorus atoms are P31, right? So if the mass number is 31, you'll notice that the mass, an AMU, of a P31 atom is 30.97. This is very common. This is very common. What you'll see is it will be just a little bit less than the mass number. So very close, but just a little bit less than. So now I can actually link this to what we see on the periodic table. If we go look at the periodic table, if you look at phosphorus, 30.97 is what we see, right? And that works out great. So it's important to understand that this is not the mass number, but this is the mass in AMUs. Now, here's the thing. Phosphorus only has one naturally occurring isotope, so it's easy to pick what's going to go on the periodic table. But what about something like chlorine, right? Remember, chlorine has two isotopes, right? Two naturally occurring isotopes, chlorine 35 and chlorine 37. So if we look at the periodic table, we'll see, keep going all the way around, we'll see that, well, that's not really close to either one, right? That's something kind of in the middle. Well, what's happening here is that this number is an average, right? This number on the periodic table, this atomic mass, is an average of the naturally occurring isotopes. So that's why carbon, even though the AMU is based on carbon, you don't have exactly 12 here, right? So one carbon-12 atom has a mass of exactly 12 AMUs, but not all carbon atoms are carbon-12, right? Phosphorus is a weird exception because all naturally occurring phosphorus atoms are P31. There's a few other atoms like that, a few other elements like that, but there's no expectation that you know what they are. What's important is that you realize that these numbers are averages. So chlorine 35, or not chlorine 35, chlorine, its block, on its block, you have a number that's an average. So this average indicates, remember I said there's two chlorine atoms, or chlorine isotopes, chlorine 35 and chlorine 37. Which do you think is probably more abundant? What do you think in a sample do you think you have more of? Now, I mentioned this earlier. It turns out we have more chlorine 35, so this average is going to be closer to 35 than 37. And an average is important for us because we're going to be working with huge numbers of atoms, so what we really care about is the average. So let's go back and take a look at how this average is, how we get this average. So, of course, what we're going to do is we're going to take an average, and we're going to take the total, we're going to add up the sum of masses of all chlorine atoms in the universe, right, divided by the number of chlorine atoms in the universe. Right? Okay, that's ridiculous. That's not practical, right? I can't go add them all up, right? So we have to have a different way of doing this. I'm going to do what's called a weighted average. So the atomic weight that appears on the periodic table is an average atomic weight. I'm going to do what's called a weighted average. So to understand what a weighted average is, let me show you something about how to do averages. So when you normally think of doing an average, right, if I have two numbers, x and y, and I want to take the average of them, what you're probably familiar with is taking x plus y divided by 2, right? Now, I'm going to manipulate this algebraically, and you should be on the lookout in case I do anything I'm not supposed to do, right? But I can break this up into y over 2 plus, or x over 2 plus y over 2, right? I can do that. And then I can take and call this x times 1/2, right? Plus y times 1/2, right? And then I'm going to take 0.5x plus 0.5y. 0.5 is roughly equivalent to, is equivalent to 50%. What we're doing, the way you normally take an average that you probably haven't really thought that hard about, right? You just add them up and then divide by the number, is you are weighting them, but you're weighting them equally, right? You're making a new number that is 50% y, x, and 50% y. So 50% x, 50% y. If you had 3 numbers, actually let's do 4. If I had 4 numbers, A, B, C, D, I would add them all up, right, and divide by 4. Well, then what I've got is 1 over 4, or A over 4 plus B over 4 plus C over 4 plus D over 4, which is really 0.25A plus 0.25B plus 0.25C plus 0.25D, right? So this is all we're weighting them equally. It's 25% for each of them. We're giving a 25% weight to every one of the numbers, an equal weight. Well, now what we're going to do is we're going to make an average of the masses of the isotopes, but we're not going to give them equal weight. We're going to weight them differently from each other because, for example, in chlorine, right? Chlorine, we have this. We have, here are the masses. So these are the actual isotopic masses right here. So this is, remember, the isotopic mass, the mass of a given isotope, is going to be very close to the mass number for that isotope, right? It's not going to be exactly, but it's going to be close. Mass number, whole number, right? Just the sum of protons and neutrons. Isotopic mass is the mass of the isotope. And then what we're calculating here is we're calculating the atomic mass, the mass of that particular element, the average. So how I'm going to do this is I'm going to take each of these numbers. I'm going to take 34.97 AMU, right, plus 36.97 AMU, but I'm going to weight them not the same, but I'm going to weight them according to the percent abundance here. So I'm going to take, and before I add them, I'm going to multiply them times their percent abundance. I'm going to multiply this times 0.7553, right? So I'm taking the percent abundance times the isotopic mass. And then over here, I'm going to take 0.2447 times its mass. So you have to pay attention to significant figures on this one. So we have to be really careful because this is one of those rare problems where we're combining multiplication and addition. So 0.7553 times 34.97 equals 26.412841 AMU. And if we look at where we would round, this is multiplication. Right, multiplication, so I'm going to look at the significant figure rule. 4 significant figures, I'll round to 4 significant figures right here, right, after the hundredths place. Then I'm going to take 0.2447 times 36.97, and I'm going to get 9.046559, right? Also 4 significant figures, but realize that for this number, 4 significant figures is a different decimal place, which is relevant to the next step. Now I'm going to add the two resulting numbers together, keeping all the numbers in my calculator, and I'll round off at the end. 35.4594 AMU. And then what I'm going to do is I'm going to round off, we don't really care about the number of significant figures. Because this is addition, we care about where the uncertainty is. So here the uncertainty in this number on the left, the uncertainty is in the hundredths place, or times hundredths. Here the uncertainty is in the thousandths place, so I'm going to round off to the biggest place, which is the hundredths. And so I get 46 AMU. Now if we look at periodic table, it's actually 35.45 in the periodic table, but it's okay. We're only off by a little bit there in the last significant figure, so it's okay. So I just want to reiterate some of these definitions. Mass number, number of protons plus number of neutrons in a given isotope of an element, right? So always a whole number, right? It's just a way to identify which isotope we're talking about. Isotopic mass, mass of a given isotope actually measured in AMUs. It's not going to be a whole number, but it's going to be really, really close to the mass number of the isotope we're talking about. Atomic mass is the average mass in AMU naturally occurring, and this is the number actually shown on the periodic table. So that's what this value is here. It is actually the average, right? And after this chapter, we're going to mostly just use the atomic mass. We don't tend to deal with individual isotopes too much. All we really end up caring about after this chapter is usually just the average. So I want you guys to give these a try. So try calculating the pause it, try calculating the average atomic masses, and you should check it with the periodic table because the periodic table should have the correct number. Okay, so I'm going to take, for lithium, I'm just going to take oops, I don't know why that happened. 0.0742 times 6.01 AMU plus 0.9258 times 7.02 AMU. So I'm going to do each of these separately. So 0.0742 times 6.01 gives me 0.445942. Again, three significant figures. I'm going to round there. Then I'm going to take 0.9258 times 7.02. Again, three significant figures. 6.499116. I would round here after three significant figures. So then I'm going to add the two together, 0.445942, and get 6.95, because that's where I need to round according to this number here, AMU. Okay, and let's check that with the periodic table. So lithium is, 6.94, and we got 6.95. So again, it's okay if we're off because we're rounding in that last significant figure. That's all right. So magnesium, same basic strategy. I'm going to take 0.7899 times 23.99 AMU, right, plus 0.1000 times 24.99 AMU plus 0.1101 times 25.98 AMU, right? So 0.7899 times 23.99 gives me 18.949949.701. I should round to four significant figures, which is going to be there. The next operation gives me 2.499, right? So there's where I'm going to round after four significant figures, and 0.1101 times 25.98 gives me 2.860398. Again, four significant figures right there. So 18.949701, 2.4991, should be a plus sign here, plus 2.860398, and so I get 24.31 AMU. Check the periodic table. Again, off by, I'm rounding, I'm getting one higher in that last significant figure, it seems to be, but that's okay. Okay, and that is average atomic mass.